is presently working as Associate Professor of Physics at Kalindi College. She has about 23 years of teaching experience and about 25 years of research experience. Her field of specialization is accelerator-based experimental atomic physics. She was awarded DAAD, the German Academic Exchange Service Program Sandwich Model Fellowship, for doing the PhD at GSI in Germany. Her PhD was awarded in Germany only. She has been awarded Indian National Science Academy, that is INSA DST Long-Term Visit Award under the Indo-German bilateral program in 2012. She has been involved in the guidance of 3 PhD, 3 postgraduate, undergraduate research projects.
Pushpa, your voice is hardly audible. There is some problem with the audio, I think, today. It's not audible at all. So, okay, we can always cut my introduction short. I can just speak 2-3 sentences and wind it up. So, those who are interested can read my bio note. I'm going to take several lectures with you. Therefore, this introduction shall keep appearing. So I'm interested in education and teaching, and service to science education is my passion. I am very much interested in guiding students for all kinds of research projects, starting from undergraduate to postgraduate and beyond, and also research doctorates. So that's my passion. I'm to several agencies like NASI. I'm a member of NASI, of IAPT, Indian Association of Physics Teachers, Indian Society for Radiation Physics, and so on. And all these science societies are there only for faculty and students to join in and contribute to the development and growth of science in our country. These series of lectures arranged through National Academy of Sciences, India NASI Delhi chapter is also an initiative in that direction only, to popularize science and to establish science as something very, very dear in the hearts of our students. And so with these words, and I have research publications in international and national journals. I've attended international conferences and so on. And having traveled far and wide, I have just realized that the way our country can grow further is only by embedding science in the minds of our students, more and more students taking up science and then applying science to the benefit of our society. And all the initiative now and in the future shall be to help students establish themselves in physics, in other fields of science also, interdisciplinary fields, so that they can bring use of that knowledge for the growth and development of our country. So that's it. Thank you. And I would now like to, so the attendance link is there for the students to fill. And now, may I share the screen now, Dr. Varsha?
Yes, ma'am. Yes,
Yes, ma'am. Just a minute. You may now share this.
Is my screen visible?
Yes, ma'am.
So the 1 minute. Is this slide visible? White background, statistical mechanics?
Yes,
ma'am.
Yes, okay. So I'll now go into the slideshow mode and start my slides. And before I do that, I would like to speak a sentence to the students. I'm not able to see the chat box. Please just let me know by looking at the attendees box. Students, just raise your hand if this is the first time you are attending a statistical mechanics lecture with me. So I would like to see how many, I just want to see the number of hands.
Ma'am, it's increasing.
So my question, I'm repeating my question. Is this the first time that you're attending the statistical mechanics lecture with me? Because I delivered one earlier also. So the number is rising, and that means a fraction of the students are listening for the first time statistical mechanics from me. There have been other lecturers and there will be more. There's no doubt. That's it. That's it. Enough. Enough. I've got an idea. I've got an idea. Okay. So since that is the case, that about one third or so students have raised hands and have expressed that this is the first time that they are they are listening to the statistical mechanics lecture by me. So I will have to take 2-3 minutes to first reintroduce what I introduced in my last lecture a few days ago and move further. So there's a group of 4 teachers who are teaching statistical mechanics to you in this particular course. You have been introduced to 2 of them, and also myself, the third one, and then there'll be a 4th one also. As a team, we are explaining both the concepts and numericals to you. So the combination of the 4 teachers, their PPTs, their material, their lectures, their videos will complete the concept of statistical mechanics with you in concept as well as in numerical. And in my previous lecture, I had introduced 2-3 things. First of all, the first thing that we have to remember the moment we look at statistical mechanics is that the statistical mechanics is one field of physics which is valid and is applicable in all the subfields of physics, like atomic, like molecular, nuclear, particle, solid state. In all these fields which I had just mentioned, statistical mechanics is totally valid and is applicable and is indispensable. That means you cannot understand atomic, molecular, nuclear, particle, solid state physics without understanding or without grasping the concepts of statistical mechanics properly, because every of these phenomena which take place in the subatomic level, and also at the molecular level, you will have each and every phenomena being guided by the statistical nature of the phenomena.
Punita ma'am,
The
I
statistical
request
nature is,
you for the slideshow mode.
yeah, one second. Is it okay?
Yes, ma'am. It is
Actually, I had
fine.
not yet started going to the slides. So I was speaking and recapitulating what I did with the students in the last lecture. So statistical mechanics is an indispensable subject. It gives a special insight, a special perspective to all the subatomic physics fields, which I mentioned just now. In statistical mechanics, we are dealing with the statistics of each and every phenomena. What is statistics? Statistics, we understand that we observe a particular phenomena, we take observations, and then we look at the nature of the phenomena, either with respect to time evolution or with respect to some particular parameters evolution. Some parameter has to evolve itself in a particular direction, increasing or decreasing, some particular parameter, and we are going to observe a particular natural phenomena, subatomic phenomena of these fields, and we try to note the statistics of it. Now, one example which I gave was that, like in a school level, you are asked to calculate the statistics for a class of students getting certain number of marks for a particular subject. And then you make a kind of a table, you write down the marks of each and every student, and you try to find out the average marks, the highest marks, the lowest marks, and so on. So that was the first example of statistics that you got. What do we do in physics about it? In physics, we are observing natural phenomena, and we are trying to observe natural phenomena and trying to explain it with the help of the laws and the understanding of physics that human beings have tried to attain till now. Okay. So then the second concept which I revised was that you must be well versed with the concepts of probability. Why probability? Once again, because every physical phenomena is probabilistic in nature. You cannot name any phenomena which does not have probability attached with it. The probability, when it repeatedly gives you an answer of either 0.9 or 1, you reach to a definite conclusion that yes, this particular phenomena is very probabilistic and will definitely occur. This particular phenomena is definitely probabilistic and will definitely occur. Why and how can we say this? We can say this only if we have done repeated observations for that particular phenomena, noted the observations, and have drawn an inference. In case we do not do that, we cannot say for sure what is the probability of the occurrence of any event. Now, event can be anything. Event can be anything. It can be something as simple as striking of a ball by a bat during a cricket match, by a expert person like Sachin Tendulkar or Dhoni or anybody. So any expert person who is expert in cricket, the probability of hitting the ball with the bat, you'll say one only. Yeah. Now we come to the subatomic level. What is the probability that the electron in the Bohr-Moitum model will jump from a higher orbit to a lower orbit? What is the probability that an atom in a higher orbit will jump to a lower orbit in a Bohr atom model? I've gone to the subatomic level. Or I can ask, what is the probability that this particular hydrogen molecule will show rotational motion, translational motion, etc. So you see, I just give you two examples. There can be n number of such examples. And the concept that we have to remember is that in physics, everything is probabilistic in nature, and hence an understanding of probability is essential. Now let me move a little bit with the slides. So we're going to study statistical mechanics. We understood the word statistical, and we now understand the meaning of mechanics. The first time we think of mechanics is in class 11 or in class 9, where we are first of all introduced to Newtonian mechanics. And Newtonian mechanics is understood as a classical mechanics. It is definitely different from quantum mechanics. Now, what is in motion here? What exactly is in motion when we are talking about statistical mechanics? We have to remember that this is a question, and as we move forward with the subject in several lectures, we have to keep on asking ourselves that the system that we are considering right now, whether it is Maxwell-Boltzmann system or Bose-Einstein system or Fermi-Dirac system, what exactly is moving? And it is moving with respect to which parameter? So statistical mechanics has two main portions, classical statistical mechanics and quantum statistical mechanics. The quantum statistical mechanics further is divided into two types of statistics, the Bose-Einstein statistics and the Fermi-Dirac statistics. This is the general classification of statistical mechanics, and the statistical mechanics is also having a separate portion shown here in the orange rectangle, radiation, which must be dealt both in the classical and in the quantum ways. I repeat, statistical mechanics here must be considered in both its forms, classical as well as quantum, when we are dealing with radiation. So for any student who wants to become a master in statistical mechanics and understand all the beauties of statistical mechanics, must understand that the statistical mechanics must be dealt in three different ways majorly. That is classical, second is quantum, and the third is radiation. Radiation is definitely dealt in both ways, classical as well as quantum. So the moment we come up across any particular system, the moment we come across any particular problem in statistical mechanics, the first question we have to ask is this bifurcation, this classification, where is this system belonging to? Is it radiation? Is it classical? Is it quantum? And if it is quantum, whether it will follow Bose-Einstein or whether it will follow Fermi-Dirac statistics. Unless we are absolutely clear about this classification, which is shown in this slide, your interpretation can be grossly wrong. So I'm repeating, you have to identify which system are you dealing with and whether that system is falling into the category of radiation. If it is falling in the category of radiation, then will it be dealt with classically or will it be dealt quantum mechanically? What is expected of in that particular system, number one. And if it is not radiation, then the system that we are considering, should we follow it like classical statistical mechanics, or should we follow quantum statistical mechanics? I hope that's clear. So in case it is not clear, you can give a feedback and you'll get a revision. It's not a problem. Now, as I said, 4 teachers together are going to cover this subject for you. We are going, because of the feedback of about 70% of the students, we'll have more lectures on statistical mechanics. And so this will go in a very detailed manner. And some other subjects, depending upon resource persons, will also go in a very detailed manner. Now, next is contents of statistical mechanics. The first part deals with classical. The first part deals with classical. Now let us look at what I've written on the slides. The classical statistical mechanics, the first thing, as I mentioned, is that we must have a thorough understanding of the probability. The probability for occurrence of any particular event. Now, the moment I said event can be anything occurring within the domain of physics. Whatever is occurring in the domain of physics, that is called an event, we know that, but we must be absolutely sure whether it is an independent event, whether it is a dependent event, or whether it is a mutually exclusive event. In case we have confusion regarding these three different types of events, our first work is to clarify that, classify that properly, and get these concepts very clear into our heads. In the following 2-3 slides, I'm trying to tell you that while you're approaching and understanding the statistical mechanics course, these are the few things that must be always in your mind as questions while dealing with a particular subject. In case you are able to keep these points in your mind, these questions in your mind, then the understanding of your subject will be much deeper, and you will be suddenly able to see entire subatomic physics from the eyes of statistical mechanics. From the eyes of statistical mechanics, that means an electron, for example, in the solid state physics, an electron is an electron which is following Bohr atomic model. It is following Sommerfield's theory also. That electron is embedded in a lattice and hence is following entire solid state physics, which is again probabilistic in nature and hence guided by statistical mechanics. The same electron in the subatomic field is guided by quantum mechanics, and hence the dual nature of the matter, where the particle nature is converted or thought of as wave nature, should be very clear to us. So that single electron sitting in any element, single electron in any element present in the periodic table, just a ponder over it makes us realize that simultaneously we must understand that apart from its wave nature and matter duality, that means sometimes particle nature and sometimes wave nature, we have to remember that the entire behavior of the atom as a single entity, the entire behavior of the atom as a single entity, entire behavior of the electron as a single entity, and the entire behavior of the electron in combination to the neighboring electrons is also guided by statistical mechanics and quantum mechanics simultaneously. So the physicists say that once you understand quantum mechanics and statistical mechanics, then these boundaries of solid state physics, atomic physics, molecular physics, nuclear and particle physics fade away. They fade away because now your system poses to you as a system following a certain nature or behavior, and observation of that nature or behavior leads you to decide whether you will apply this kind of statistics or that kind of statistics. And when you have reached to a conclusion, then the way the particular system will behave is very clear to us. And then nothing is left as a mystery to us. I will repeat this sentence later and I will explain further what I mean by this. So the first thing is probability. For every particular system that you're talking about, we must think about which particular behavior is probabilistic in nature. Which particular behavior is probabilistic in nature. For example, if I take a boson, will it have a spin up or spin down? Is it valid? Is it applicable? These kind of things must go on in our head while we are preparing to understand this beautiful perspective of physics. The second thing is, what are macrostates and microstates? My lecture is also a kind of a lecture which is complementary to the two other lectures which you are hearing. However, if you fit everything together, you will understand it much better. So what are macrostates and what are macrostates? And then the definition and the examples of all statistics for macrostates and microstates must be clear to you for all the three different types of statistics. What are the three different types of statistics? Classical, and within quantum, Bose-Einstein and Fermi-Dirac. Three kinds of statistics. The definition and the explanation of macrostates and microstates differs in all the three kinds of statistics. So for each system, we must focus our attention on what are the macrostates, what are the microstates, how are they differing from that case, how are they differing from the other case, and so on. Third, degeneracy. You already heard what is degeneracy. The degeneracy, its meaning is, in the simplest way, it means that more than one particle state has the same energy. More than one particle state has the same energy. Now, example, I will again take Zoom example. You are attending a webinar right now. There are 500 places in this Zoom webinar, and this system is non-degenerate. This system is non-degenerate. Why? Because each particular allocation of a participant is unique, and no two participants can enter the same allocation of a seat in this webinar. This webinar has 500 seats, and 500 seats must have individual designations, must have individual participants. So for example, if you log into this Zoom webinar, these lectures from two different IDs, then even though you are same, your two different IDs will be occupying two different places in that number of 500, and so on. So if I log in through three different devices, a phone, one laptop, and another laptop, or the same laptop with three different email IDs, and if I can have multiple devices, I can attend the webinar from three different devices. However, the Zoom will be counting you as an individual participant. So this system of webinar, teacher and student participation, teaching and learning process, is a non-degenerate system. Therefore, in each system that we talk about in statistical mechanics, the concept of degeneracy should be very clear to us. Are more than one particle states having the same amount of energy? Yes or no? This is the third most important question that must strike your mind. And in case you skip it, the probability of your misinterpreting any type of question, theoretical or numerical, would be very high. You will misinterpret if your focus is not upon degeneracy. Now, why is this degeneracy very important? We are dealing with physical systems, the subatomic systems. And in these subatomic systems, the most important thing that we want to deal about or deal with is energy. If you are a physicist and you want to understand a system, if you are a physicist and you want to understand a system, what are possible questions you will ask? Suppose you don't know much and you just want to do something, anything. You observe and you want to understand that system. Then from lower level, you'll say, what is its mass? Okay. Number one, what is its mass? Then second, you'll say, is it charged? Does it have charge? Yes, no. So mass, charge. What is the third quantity you ask? Is it in motion or is it at rest? So if it is in motion, whether it is translational or rotational. If it is rotational, does it have angular momentum? Is it suffering a torque? And so on. Next, what do you ask? You have asked everything within Newtonian mechanics. If you have asked everything of these questions, mass, velocity, charge, then you have already tried to understand the state of that physical system from the eyes of Newtonian mechanics, from the eyes of electrostatics, and if you have also noted the motion, then electrodynamics. And if you ask about the magnetic status of that particular system, then you know about its magnetostatics and magnetodynamics also, electrodynamics also. What is further? This is all on the macro level. It is all on the macro level. And now we go down to the subatomic level. And the first question that we must ask is that, what is its angular momentum? What is its angular momentum? If we don't ask that, we will not reach any further. So whether it is subatomic or whether it is classical, whether it is macroscopic at a higher level or whether it is microscopic at the subatomic level, the degeneracy is nothing else but the fact that we want to understand the energy of the system. Suppose you have a cricket ball or you have any ball or any macroscopic object. What do you want to understand out of it? You want to understand mass, you want to understand velocity, charge, yes, no, magnetic properties are available, yes, no, whether it is at rest, yes, no. And then what do you want to get out of it? You want to get out energy. And if you know the energy, then obviously the second question comes, is it kinetic, is it potential, is it conserved, is it not conserved, and so on. What is it in the subatomic system? In the subatomic system, again, we are bothered about the energy of the system. Why energy? Because energy is the main parameter which will guide many things. Now, please just think a little bit about quantum mechanics. The Schrodinger wave equation. The Schrodinger wave equation, H psi is equal to E psi. Psi is the wave function that we are associating or that we have considered, or the wave packet that we have considered for one particle. What are we doing on it? We're doing the operation of using a Hamiltonian on it. H psi is equal to E psi. What does it give you? It gives you the energy eigenvalue of that system and returns the wave function as it is. There again, in quantum mechanics, you are trying to find out the energy eigenvalue of the system. And what is that energy eigenvalue of the system? Why should I understand energy eigenvalue of the system? What is the need? Why in the world should we understand this? And the basic answer, which actually answers the entire physics, is that the energy is the parameter which will define almost everything in the scope of physics along with angular momentum. But then momentum and energy are two faces of the same type of property. So momentum, you know, is mass into velocity, and energy in the classical is half mv square, and so on. So degeneracy is the most important aspect in any system that you want to undertake. Next is phase space. So what is phase space? In the other lectures, you have heard about what is phase space. You've seen a diagram also. So what is position space? What is momentum space? And what is the Hamilton's representation of the coordinates? Which coordinates? Let me start with phase space. So phase space means there is some space. We understand space. This particular word of phase space appears nowhere else in physics. They're only in statistical mechanics. The position space is very simple. Where is the particle or where is the system located? If it has several particles, then what are the positions of those various particles? What is momentum space? It is the space in which you can designate a particular momentum to a particular particle. The particle constitutes a bigger system. The particle constitutes a bigger system. A system can be anything. You can start with the simplest and the one that you like. Try to understand statistical mechanics by just one type of system that you like to understand, say a gas of particles. So what is the space which is called momentum space? Every particle has got a mass, it is moving, so mass into velocity. And if we can designate the three coordinates x, y, z in our normal coordinate system as px, py, and pz, then the momentum space is the space in which each particular point will tell us whether that particle has a momentum. Px is equal to how much, py is equal to how much, pz is equal to how much. Just as from lower level, from the lower classes, you know very easily how to designate the position of a particular particle in a simple XYZ diagram. In a simple XYZ diagram, you are locating the position. In lower classes in 2-dimensional and in higher classes 3-dimensional. The combination of this position space and the momentum space is called phase space. That means if I now look at the phase space, then every particular particle can be designated there, not only about its position, but also for its momentum. So let's say I have a phase space and it has got 3 coordinates of the position space and 3 coordinates of the momentum space. And if I now put a point in this phase space, then that particular point is describing both the position and the momenta for that particular particle, which is within a particular bigger system. So if you are considering a gas of molecules, then the molecule's position and momentum is completely defined by the phase space. Translate ourselves to subatomic world. Let's translate ourselves to the subatomic world. We are talking about, if you are talking about electron, subatomic, then again, the phase space will give the position of the electron and the momentum of the electron in the classical concept only. In the classical concept only. And if you would now apply quantum mechanics, then you have to remember that just as in quantum mechanics, the probability of finding a particular electron somewhere in space is given by mod chi square. Integration of mod chi square is equal to 1. Similarly, you have to find out the position here. So you see, it is the same system which has to be observed from all particular sites. All these points we would be covering in detail along with other teachers. What is Hamilton's representation of coordinates? You have had a course of classical dynamics by now, and therefore I need not tell you what is Hamilton's representation of coordinates. So if a particular system in which there are particles, you can take a gas of molecules. So you can take one molecule, or you can take an atomic gas and consider one atom of a gas, Then in that case, you can denote the position by a coordinate, say Q, and you can denote the momentum by, say, P. Then the Hamilton's equations, which you know very well, the Hamilton is dependent upon Q and P, and therefore the Hamilton's derivative equations tell you the movement of the coordinate space and the movement of the momentum space. We'll come to that in detail. Why have I written it together? Why have I written it together? I've written it together because when you are understanding this subject from one particular book, it might be that they just do not speak about Hamilton's representation of canonical coordinates and describe the phase space only with its position and momentum. However, when you go to any other particular book, I'm giving you a ladder today also, you will realize that the phase space is defined only through the Hamilton's representation of canonical coordinates. The position and momentum are canonical in nature. And the entire statistical mechanics, the ABC of statistical mechanics, starts with Hamilton's representation of coordinates, which are somehow not mentioned in each kind of reference material that you might use. However, this is the beginning point, it's the ABC. Next, entropy and thermodynamic probability. The field of statistical mechanics is not bothered about what is happening to a single atom in a system of several atoms. It is not bothered about what is happening to a single molecule in a system of large number of molecules. Thermodynamics ends with a relation of, with the third law of thermodynamics, and it gives you a relation about entropy also, an understanding about chaos, about disorder, and the word entropy immediately triggers in your brain the concept of chaos, disorder, its connection to other quantities of thermodynamics like heat and temperature. Statistical mechanics is one way ahead of thermodynamics. And the bridge between thermodynamics and statistical mechanics is the famous Boltzmann entropy equation, S is equal to K ln W. I'll come to it much later. So what is it in statistical mechanics that we are going to do, which we did not do in thermodynamics? Now, the beautiful thing is that we in statistical mechanics are only bothered about the behavior of the system as a whole, although we have complete understanding of macro and micro states. One point of confusion in the minds of several students, even after doing post-graduation and so on, is that we are looking at microstates. Then we are saying we are only bothered about macroscopic behavior. What are we doing? Are we looking micro level or we are looking at macro level? What is it that we want to understand out of a system? When we are having any particular system, ideal gas molecules or any particular kind, or a system of bosons, system of fermions, electrons, neutrons, anything, take any example. The distribution of micro and the macro states is extremely important, because only that gives you the idea of the most probable distribution. It gives you the idea of most probable distribution. Without looking at the micro and the macro states for any particular system, we cannot reach a conclusion about the thermodynamic probability or the probability of most probable occurrence in a system. And unless we do that, this probability of the most probable probability, that means you have a system, okay, and you arrange it in a certain manner. You have a system with, say, 10 particles, which you can arrange in different manners. You can arrange, or you're observing a natural phenomena in which the system by itself is changing its state. For example, if you're observing, if you had some vision, imaginary vision by which you could actually see what electrons are doing in an atom, then you would observe, yes, now the electron was here. Remember, there has to be some perturbation. A neutral atom and electrons within a neutral atom will do nothing else except move around in stationary states. You can represent them by the Bohr atom model or do the Schrodinger wave equation concept in your brain. So introduce a perturbation to that atom. It has got electrons inside it. I'm not going inside the nucleus. I'm looking at only the electrons around the nucleus. And I am observing what are the electrons doing because of that disturbance to the system. Some disturbance has been introduced in the form of potential, which you are including in the Hamiltonian equation, Schrodinger wave equation, the Hamiltonian. Or you can disturb its energy and so on. You can do several things. And we start observing. And when we start observing, we see, what is happening? This particular electron is moving there. Now there is a vacancy in this shell. Now there is a transition and so on. So this whole particular procedure of this imaginary vision that you can actually see the movement of electron going on within an atom, what are you trying to observe? You are trying to observe what is the most probable way in which the electrons will behave in a particular situation. I repeat, what is the most probable way in which the electrons will behave in a particular situation? What is the situation? This English word of situation actually means, well, how would they behave in a certain case of a perturbation introduced from outside? So perturbation can be, you can just disturb the neutral atom by providing it with certain amount of energy. The moment you supply energy, the neutral atom has got an excess energy, the electrons will get excited, they'll go to the higher levels. And if they go to the higher levels, they'll leave a vacancy down. And if there is a vacancy down in the lower subshells, any atom can drop down from the higher level to the lower level. We learned all this very well in class 12 itself. This very simple model is the best example to understand that any kind of perturbation can lead to a system moving in different ways. What is the most probable distribution? If I do it repeatedly, will the same shell get activated to get a vacancy? Will the same shell get a vacancy and will the same electron jump down? Or can any other shell's electron jump down? What is the probability that the electron in L shell will jump down? What is the probability that an electron in the M shell can jump down to the K shell and so on? So I can go on and on, keep on doing my experiment, and with my imaginary vision, I can note down how is the electron behaving in the situation of an external disturbance, which is nothing else but providing energy from outside. Manifested as the part of a potential that enters the Schrodinger wave equation. H psi is equal to E psi, the Hamiltonian, takes care of each kind of perturbation introduced in all kinds of subatomic systems. And mind you, the moment we talk about subatomic systems, we'll have to take care about all this. So these are few things which I'm sharing with you as we move forward. If your perspective is altered and you wear the spectacles of statistical mechanics and quantum mechanics on the two sides of your eyes, entire physics becomes absolutely easy and very logical. And therefore, it is reduced, the remembering of physics and the enjoying of physics increases, and the mathematical part becomes a very beautiful complement to this beautiful nature that we have, which we try to understand through laws of physics. So entropy and thermodynamic probability, relation and its consequence. What is the consequence of this relation between S is equal to entropy is equal to K, Boltzmann constant, S entropy is equal to Boltzmann constant K, ln, which is logarithmic to the base of E multiplied by thermodynamic probability. Dynamic probability. Why not any probability? Thermodynamic probability, because statistical mechanics will not initiate itself unless the system that you are considering has reached perfect thermodynamic equilibrium. That is why the word thermodynamic probability, not just any probability, probability of tossing a coin. No. We're talking about thermodynamic probability. This will be manifested, or this will be required, or this is valid because the system has reached thermodynamic equilibrium. What is thermodynamic equilibrium? The thermodynamic equilibrium must involve mechanical, chemical, and can somebody answer? What is the third equilibrium that must occur? What is the answer? I mean, I can't see the, may I, what is the name? Chat box. I cannot see the chat box. Can somebody read it out for me? Hello. Am I audible?
Yes, ma'am.
Yeah, you are
Yes.
audible.
Yeah, so can somebody write down in the chat box? I'm unable to see the chat box somehow. I don't know why.
What is it that
Yes, ma'am,
you
you are
want?
audible.
Do you want?
No, I just want to read the answer from the chat box. I'm asking what is the third kind of equilibrium that must exist?
Yes,
Is there an answer?
thermal.
Yes,
Right.
thermal
Right.
I'll not answer this. You have to know what is thermodynamic equilibrium.
and
I can
chemical.
tell it
Some
is
are writing chemical equilibrium as well.
chemical, thermal, and mechanical. Three.
Mechanical, yes.
Yes, exactly. Mechanical, thermal, and chemical, when all these three processes have reached an equilibrium, we say it is a thermodynamic. You have to see there is this word dynamic. Mechanics has to be involved. And thermal has to be involved. And temperature and chemistry is directly related, so chemical is involved. Only when a system is completely thermodynamical equilibrium status, then only we start applying statistical mechanics. Never under non-equilibrium conditions do we think of statistical mechanics. So statistical mechanics is not bothered how the system reached the equilibrium. What was the procedure of reaching the equilibrium? Was it quasi-static, or whether it was slow, or whether it was fast? It's least bothered. Statistical mechanics starts thinking only when the system has reached thermodynamic equilibrium. That means chemical, thermal, and mechanical equilibrium has been reached. And then, although statistical mechanics is bothered about macro and micro states of a particular system, it is not bothered about the individual behavior of the constituents of that system. It is not bothered. Now, this is a bit confusing because we do take example of, let us consider a gas molecule. And then we say we are not bothered about the gas molecule. So an obvious question to the student's mind is, are you bothered or you're not bothered? Please make it clear. The question is, we are not bothered. The statistical mechanics is trying to give the behavior of the system under certain conditions and is not bothered what the individual constituent particle, whether it is an atom in an atomic gas, molecule in a molecular gas, electron in an atom, neutron in a nucleus is doing. It's not bothered. It's bothered about the macroscopic behavior of the system. And therefore, the consequences of entropy and thermodynamic probability relation, S is equal to K ln W. W or omega is the symbol that we use to designate thermodynamic probability. And which probability is there? Which probability are we talking about? We're not talking about any probability. Obviously, every event has several probabilities. Every event has several probabilities. If you're connected to the WhatsApp group, the probability of getting a Zoom link for this webinar is 1. You will get it. If you've not connected to the WhatsApp group of this particular webinar, the probability of getting a link for this particular webinar is half, or maybe even less, because you're not connected with us. So thermodynamic probability means the probability of the most probable occurrence. Back to my example of atom. What is the most probable way in which the electrons are making transitions from higher levels to lower levels? If I do this disturbance, perturbation again and again, what is the most probable distribution? I keep on noting. And then I find that out of the 100 observations, around 60 observations are the same. And this is my most probably occurring distribution of the system. This is the most probable occurrence of that distribution of that particular system. Distribution of what? The distribution of electrons in various shells here. And in every case that we consider, this thermodynamic probability is the most probable occurrence or the maximum ways in which you can arrange a particular constituent elements in a system. Example, very simple example. You take a box, you make bifurcations inside it, then you take balls, red, blue, green. The most simplest example to get the concept right into your head. If I say that, okay, the box has 3 compartments, now arrange the balls. You can do it in several. I have not put any condition. You can put all 3 into 1, you can put 2 in 1, you can do red, blue, blue, green, red, yellow, and so on. Several ways. What is the most probable way in which it can be done? That is the thermodynamic probability. And the example of these balls in a box is only a concept or an example to understand. Here, there is no thermodynamics actually involved. But this is a concept which we can understand through this simple example. Then we come to Maxwell-Boltzmann distribution law. The first question that comes to the mind is, why Maxwell? There are so many distribution laws. There can be so many laws in physics. Why do we choose Maxwell-Boltzmann distribution law? Is it because the word Boltzmann is there and Boltzmann gave the S is equal to KL and W relation? No. What is so special about Maxwell-Boltzmann distribution law? This is a question which 99% of the students, even after post-graduation, do not dwell upon. Why do we have this particular portion in our understanding of classical statistical mechanics? What is the distribution? What is this distribution that we are talking about? We're talking about distribution. Whose distribution? Distribution about what? Which quantities are being distributed? And amongst what? Is it same or is it different from the Maxwell-Boltzmann distribution law that we study in kinetic theory of gases? In kinetic theory of gases, which you are initiated in class 11, you are trying to study an ideal gas. And before you study it, you take n number of assumptions. It will not interact with each other. It will not do this. It will not do that. And so many assumptions. So kinetic theory of gases starts with assumptions. And those assumptions are way out of the physicist to avoid complicated equations, which will automatically crop up the moment you take mutual interactions between the gas molecules that you're considering in kinetic theory of gases. Ideal gas molecules you're considering in kinetic theory and you're doing Maxwell-Boltzmann distribution. Is this law different from that? No, the law is not different. Law is law. Yeah. Physicists are very clear about their laws. Law is there. There are assumptions that separate thing. There are exceptions that are separate thing, but a law is law. So the Maxwell-Boltzmann distribution law is the same as that it was in kinetic theory. Well, if it is the same, then why are we rereading it here? What is it that we want to understand through this perspective of statistical mechanics? What is it that we will understand more after going through this? So the answer lies in this distribution. And then I move forward further in this particular lectures, not this today's lecture, but the next lecture, we will dwell upon that why is this distribution the first distribution that we apply in the case of a classical case. We are still on statistical mechanics, the classical one. We will consider classical cases and we will, as a happy-go measure, we'll start with gas molecules, which we have already done in kinetic theory of gases. So what is understood clearly is that though the distribution is the same, there is something about it because of which it is being reread here through a different perspective. What is it? Where is the thermodynamic probability connected to this distribution? And once again, which quantities are being distributed? And what is the distribution all about? Then partition function, you're going to hear a lecture, complete lecture on partition function. What is partition function? Why is it required? Is something partitioned? The moment you hear a word, the first thing is partition function. Something is going to be partitioned. Is something really partitioned? And if it is yes, that amongst which parameters is it getting partitioned? And when this partition function, you all are aware, being graduate and postgraduate students, this partition function is different for classical statistical mechanics, for quantum statistical mechanics, and then within quantum statistical mechanics also, you alter it in different situations. So this partition function, what is something being partitioned? One must be, these are the questions which must quickly race through. You open up anything with statistical mechanics and these questions about which I've been talking about for the past half an hour should race through your brain within less than 5 seconds. And if they do not, you will not understand the depth of it. You might be able to do numericals, but you'll never get the feel of it And when you start living and enjoying physics as you enjoy your favorite breeze of air or anything, it goes into your system completely. So I will not answer these. The next lecture is about this. The thermodynamic functions of an ideal gas. You see, chronologically, first thermodynamics was understood, and then slowly classical statistical mechanics, and after the advent of quantum mechanics, quantum statistical mechanics was established. Should we not study statistical mechanics first and then try to see what is thermodynamics? No, we can't do that, because as I said, unless you understand quantum, you cannot understand quantum statistical mechanics. So you have to wait. Ideally, thermodynamics, which is bothered about the behavior of the system, and statistical mechanics, which is bothered about the macroscopic behavior of the system, thermodynamics and all its laws, all its corollaries, all its equations, all different quantities that you calculate in thermodynamics are nothing else but a corollary of your statistical mechanics as special cases. So statistical mechanics is the way to understand a natural phenomena because it is based on statistics, and then reach thermodynamics through it. And then reach through thermodynamics to it because it's a logical conclusion. For certain cases, we have exceptions, and for certain cases, we can show directly how statistical mechanics leads to thermodynamical equations or corollaries or the details that we learn through that particular subject. Let me, one second, the slide is not moving. So classical entropy expression, how is it different or similar to that of thermodynamics? This is what we have to dwell upon. And as I mentioned, that when we move further in statistical mechanics, we talk more about entropy of a system. And in special cases, we talk about entropy in a system of two gases before and after mixing. Entropy in a system of two gases before and after mixing. So the obvious question that comes to the mind is, what is self-mixing? Why is it necessary to ponder on this? Suddenly out of the blue in classical statistical mechanics, they start talking about mixing. Why should we talk about mixing? If you're talking about mixing, that means you're mixing two gases. Okay, what is self-mixing? It's very clear, mixing the same gas into each other. What is the necessity of pondering on this? Why are we talking about entropy? Why don't we talk about the pressure, volume, temperature, internal energy, Helmholtz energy, Gibbs free energy, and Helmholtz free energy, and I've written it twice, I think, for a particular mixing system? This definitely, the fact that we are studying the entropy in a system of two gases, if they are same, it is self, and if they are different, then it is mixing of two different gases. There is definitely something that we understand about the entropy, which is not evidently understood while studying any of the other 7 parameters which I have written. You've seen that I've double crossed entropy. Yeah, we are focusing our attention there. That entropy will tell us how and why this classical statistical mechanics showed its limitation. So the entropy, as I said also in the last lecture, the entropy is a beautiful parameter. It's a beautiful parameter because it connects, if you know entropy and if you know temperature, then one more quantity and you know all others that you know, to Maxwell's relations. But the entropy is a parameter of chaos. It's a parameter of disorder. And for each system that you consider, this is the main parameter which gives you a greater insight. This then leads to a paradox called Gibbs paradox. And when I'll be doing this, I will not be repeating this slide, but I would like you to remember that what was the paradox and why did it arise? What went wrong? What is Boltzmann counting? Again, Boltzmann. Now, Boltzmann is everywhere. Boltzmann gave the beautiful relation S is equal to K, ln W, where K is the Boltzmann constant, which is engraved on his grave. A remarkable equation. Because of that, we have a complete understanding of statistical mechanics. If there was no Boltzmann equation, for instance, the understanding of the the subatomic world and all its physics would have been impossible. So what is Boltzmann counting? What are you counting? And why are you counting? What is the mistake that you are doing? Why did the paradox come up? Sachet-Tetrode equation. What was the remedy of paradox? And what does this equation give us as an insight to entropy of mixing? If we do not keep these questions in mind, automatically our understanding of the subject remains just factual and it doesn't seep in. I will not go into details just this for this particular slide. However, this particular slide, which is a continuation of classical statistical mechanics, will be repeated when I'll be dealing with equipartition of energy and specific heats of gases and solids. So further statistical mechanics has Bose and Fermi-Dirac, which we shall deal with when we are coming later, and also radiation. So these are the four major parts, and the lecture series on statistical mechanics will cover all of them. So classical, Bose-Einstein, Fermi-Dirac, and then radiation, both from classical and quantum perspective. It's about time for me, so I would like to wind up my lecture for today only with this ladder of books which have been long promising to the participants. As you can see, I've tried to show a ladder, and obviously, as you can see, the topmost right-hand side is the highest step of the ladder. The ladder of books for the statistical mechanics. If you really want to understand this subject in the coming 2 weeks completely and be thorough with it, then you have to work in resonance with us. In the lowest part of the ladder is Concepts of Modern Physics by Beiser. Second, this is a world famous book for the just beginners of the graduation. However, do not think that it is a low level book. Its understanding itself, even for postgraduate students, some of the sentences can surprise you. There is Thermodynamics by Garg Bansal and Ghosh, or Thermodynamics by Loknathan and Gambhir. You move up, you read Statistical Mechanics by E. Guha. And this particular book, one can read in leisure as if one is reading a novel, and you see the beautiful perspective by which the statistical mechanics becomes a very logical subject to you. It unfolds itself in a different way altogether through this book. You understand it more, and if you understand it more, as I said in the last lecture also, the mathematics is very, very simple. It employs just differentiation, integration, and application of some standard integrals. There is no rigorous, detailed mathematics in this particular subject compared to your other courses which require a lot of mathematical physics. Then you move up and you read treatise on heat by Saha and Srivastava, and the Saha word here is designating our famous scientist Meghnad Saha, right? And this book is, though rarely available, not easily available, but most of the libraries have it, and it's a beautiful way of understanding all these concepts. And once concepts are understood, then as I said, mathematics is just nothing. Next is Thermodynamics and Statistical Thermodynamics by Sears and Salinger, which has been partly used by other lecturers who have been taking courses with you in lectures with you in this particular webinar series. And then Fundamentals of Statistical Mechanics and Thermodynamics by Frederick, Rife, and Berkeley series. So the author is the same, but one is McGraw-Hill publication, the other is Berkeley series publication. After you have done this, then you can move on to Statistical Mechanics by Huang. World over, statistical mechanics are read and understood by these books only. Sears and Salinger, Rife, both the series, Huang. I forgot to mention Patria, but between these three steps is where Patria sets in for the classical statistical mechanics, not for quantum. Then Statistical Mechanics by Meindl and by M. Kirdar, and there are some authors, but this is more than sufficient. You start at the undergraduate level and you stop at the postgraduate. In fact, if you do understand Huang, Meindl, there's actually no need to even go to M. Kirdar, who is a lecturer in the MIT, and his lectures and books are also available. Dr. Bindal.
Yeah, thank you, Dr. Punita. It was really nice, and you have cleared the basic concepts of statistical mechanics to the students. And I think our next speaker, Dr. Sanjay, is also with us. He has joined.
Okay, so I have to stop share, right?
Yeah, yeah.
So Dr. Sanjay is already here and he is beautifully explaining the numericals and the concepts. But my talk today was inspired by the number of questions which were too basic in nature and were repeatedly asked in the question answer box during Dr. Aditya Saxena's lecture and during Dr. Sanjay's lecture also. So I thought that it would be then appropriate that instead of just rushing through the particular content and doing only numericals, which are beautifully done by my colleagues like Dr. Sanjay and Dr. Aditya and also Dr. Sham from tomorrow, I could then focus upon clearing your concepts. So those students who are really understanding what I'm trying to say and who are interested in understanding this subject for once and for all, well and nice and beautifully, you should start reading immediately the 3 books I have mentioned. So I'm going to now today evening send you all on WhatsApp just as you have received everything, books, etc. and PPTs on WhatsApp. And you start reading immediately so that when I take up the next lecture and you have next lecture, you work in resonance with us and you will be well versed with this subject. So with these words, thank you very much